It's okay. I won't take it personally. So hello, everyone. I think we'll get started. So today, well, this lecture, well, we're in Comp 30. Come on. We're in Comp 30. So let me write that. This is Comp 30. This is lecture 8, also known as 2 to the cube, or 100 in binary. And what's the date? It's September 26th. September 26th. Okay, so before we get started, hello. As usual, I'd like to start with an Italian expression, which I'm sure 90% of you, that's why you're here for. So the Italian expression of the day is the following. It's, let's see. It's this little expression here, avere le mani in pasta. So what does avere le mani in pasta mean? The literal meaning is that you have your hands stuck in some dough, because pasta can mean both dough and just regular pasta in Italian. But the actual figurative meaning is to be in a sticky situation. So to be in a sticky or problematic situation. Sticky or problematic situation, right? So sticky because dough is sticky. And so how can I use this in a sentence? So I've worked extremely hard to make the sentence relevant to you. So please pay close attention. If you don't signal a midterm conflict before October 5th, avrete le mani in pasta. So if you don't signal a midterm conflict before October 5th, you'll be in a sticky situation because I'll need to shift the weight of the midterm to the final, which may or may not be good because the midterm may or may not be easier than the final exam. So I know some of you here are taking Comp 321. I think that's the one where you do a bunch of leak code exercises. And that class seems to conflict with the midterm of the class. So if that's the case, please email me. I'm not going to just take for granted that the 321 students are going to take the makeup midterm. Please email me so I can make the necessary accommodations to get you a room so you can write a makeup. Okay. And there's two other slightly more serious announcements that I'd like to make. The first one is that the lecture 7 recording failed, as some of you know. And so I posted a recording in which I explain the notes. So that should be good enough. And the other thing is that I posted an extra note on the conversion algorithm from FAs to regular expressions. Hello. Oh, you missed the Italian expression? Yeah. Maybe at the end of class. Okay, so today's lecture will be about DFA minimization. DFA minimization. And in fact, this is going to be the topic for this week. So the topic for this week is going to be all about minimal DFA. So today, in particular, we're going to look at an algorithm which minimizes DFA. Why are people still talking? We're going to look at an algorithm which minimizes DFA. So in other words, we'll have an algorithm which takes as input some DFA. Maybe it's minimal, maybe it's not minimal, and the output is going to be a minimal DFA. Okay, so that's going to be the topic for today. Why do we want to talk about this? Well, there's some obvious reasons. Hopefully, as the good computer scientists you are, you want to, of course, avoid wasting computational resources. And in particular, in this case, you want to avoid wasting memory, right? So if you have a DFA which is overly complex, it has way too many states, you want to shrink that down such that the memory footprint it has is smaller, right? So you want to avoid the waste of computational resources, and in particular, memory. So that's today. And then on Thursday, we will actually prove that this minimal DFA that the algorithm produces is unique. So that there's a unique minimal DFA. Now, why do we care about the fact that it's minimal? Why do we care about the fact that it's unique? Why can't we just say, oh, it's minimal? Well, it turns out that if we combine the minimization algorithm and the uniqueness of minimal DFA, then together this actually gives us the tools necessary to create decision procedures for many decision problems about regular expressions, FAs, and FAs. So for instance, once we see this, we'll be able to create an algorithm for the following decision problem, given regular expressions R1 and R2 is the language described by R1 the same as the language described by R2. So the things that we're going to see today and on Thursday are going to allow us to create an algorithm which we'll know is correct and which can solve this problem. Okay, so that's the motivation for today and for Thursday. So before I talk about the minimization algorithm, I'd like to start with an example. So consider the following example. Consider the following not so minimal DFA. Not minimal DFA. So this is going to take me a minute to draw because it's not minimal, so it has a bunch of redundancies. So there's one part of the DFA, which is this cycle here. And the cycle is labeled with A's, and it has self loops with B's. Right, so at this point, I've created a very large machine which accepts the empty set. So let's add some accept states. This and this will be an accept state. And then I have some extra pieces to this machine. So I have these two parts. So I have this guy here, and I also have this guy here. Okay, so altogether, this is going to be my machine M, which is not so minimal. Okay, this is my machine M, which is not so minimal. So the question I'd like to ask here, which I'll ask myself because I know many of you won't answer it, is why is M not minimal? So why is M not minimal, he asks himself. Well, there's two reasons. The first reason is hopefully very obvious to you. It's that we have some unreachable states, right? So we have this state here, this state here, and this state here. These three states are unreachable. So what does this mean? That means that if my machine starts at the start state, like it should, then it's never going to be able to reach this part of the state transition diagram, right? So essentially, this part of the machine is completely useless. So the first reason is that I have unreachable states. So now remember what I'm trying to do. I'm trying to create a minimization algorithm. We're going to see the algorithm towards the end of the class, but to give you the intuition, right? The first thing that the minimization algorithm is going to do, it's going to fix this very easy problem. And it's just going to start at the start state, check whether there's any unreachable states, and just get rid of them. So this is an easy fix. This is an easy fix. For instance, what you could do, you can run a depth first search or a breadth first search starting at the start state, and you could mark the states which you visit. The states that you don't visit at the end of the search get garbage collected, let's say. So this is an easy fix. Let's run depth first search starting at, let's call this Q0, starting at Q0, and drop the, let's say, the unmarked states. Okay, so that's an easy fix. Very nice. So that's one of the reasons why this machine isn't minimal, but this is a sort of easy solution. The trickier bit is if we look at this machine has what I'll call redundancies for the moment. There is redundancy in the state transition diagram. This here. Okay, so what do I mean by redundancy? Well, let's look at the reachable part of this machine a bit more carefully. So this is the reachable bit. This is the bit that's actually going to do any of the work, any of the computation. So what is this machine actually accepting? Well, if we look at it carefully, we see that, we start at the start state, and if we have B's in any of the states, this doesn't affect the state we're in, right? The state we transition to. We always stay at the same state if we read a B. So it doesn't seem like B's affect this machine's behavior, okay? But if you read an A, you transition to the following state, right? And so what it seems like this machine is doing, it seems like it's counting the number of A's, right? So it counts one A, then a second A, then a third A, then a fourth, then a fifth, and then a sixth. But once it gets to the sixth A, it resets the counter, right? So it resets its counter. And so what this means is that my machine is counting the number of A's modulo 6, right? So my machine, so M is keeping track of the number of A's mod 6, right? So in other words, if I want to say what each state is responsible for, so suppose I have number of A's mod 6 in green here, then this start state is encoding when the number of A's mod 6 is 0. This one is when it's 1, 2, 3, 4, and 5. Let me finish the example. Oh, is it not visible? Is that the question? No, okay. Okay. Right. So this is what the machine appears to be doing. Its states are encoding number of A's modulo 6. Now, what is the machine actually accepting, right? Because if we didn't have any accept states, then it would just be accepting the empty language, right? It would just be an elaborate machine that accepts the empty language. Well, it looks like the accept states in this case are Q0 and this fourth state Q3. And so what you'll notice is that these accept states encode when the number of A's mod 6 is either 0 or 3, right? So you accept strings. So you accept strings such that the number of A's mod 6 is either 0 or 3, right? Well, another way of saying this is that the number of A's, so this statement here is actually equivalent to saying that the number of A's mod 3 is equal to 0. And so you can either use basic number theory to check this, or you can just look back at the transition diagram and keep track of triples of A's, right? So I start with no A's, then I get 3 A's, right? So I have 3 A's, that's an accept. Then I get 3 more A's, that's an accept. I get another 3 A's, that's another accept, and so on. And so what you notice is that every time I have a triple of A's, I accept, right? So effectively what my machine is doing is it's accepting strings where the number of A's mod 3 is 0, right? But if you remember from lecture 4, we designed a similar machine where it was that you wanted to accept strings where the number of A's mod 3 was 1 and 2. And in that machine, you only needed 3 states, and we showed that that machine was minimal. And that made sense, right? Because all you really need your states to do is to encode the number of A's mod 3 is equal to 0, 1, and 2. So effectively, what this means is that my machine M is really keeping track of the number of A's mod 3. And so this state here encodes when the number of A's mod 3 is 0. This one is when it's 1, 2. But then this one is when it's 0 as well. This one is when it's 1, and this one is when it's 2. So you have twice as many states as you need, right? Twice the number of states are doing the same, are serving the same purpose for the machine. And so that's what I mean by there is redundancy, right? There are pairs of states in the machine which have exactly the same function that serve exactly the same purpose. Okay. So the idea of the minimization algorithm, is to collapse the states which serve the same purpose or function. So the technical term for this is to say that you want to collapse states which are equivalent. So these would be equivalent states. Okay, and that's where we're going to see in a second. We're now going to sort of more formally define this notion, this sort of intuition that we have here, that these states, so this pair of states, for instance, is serving the same purpose, and so they're equivalent, and that means that I can sort of combine these two states together. Okay, so we're just going to more formally talk about this now. There were a few questions. I guess I've resolved any ambiguity. Good. Okay. So in that case, we can talk about equivalent states. So equivalent states in DFA. Let me give you a more formal definition first. So suppose I have some DFA M, which is a 5 tuple. So I have the set of states, the input alphabet, the transition function, the start state, and the set of accept states. And I have some pair of states P and Q. Then I say that P and Q are equivalent, which I'll denote P squiggle Q. If the following holds, for every string that can be defined over the input alphabet, if the machine starts at P and reads X, and it accepts the string, then if the machine starts at Q and it reads X, it will also accept that string. And vice versa. And vice versa. So this is the definition of equivalent states. So maybe this is a bit confusing at this point, so let's illustrate this a bit better with a picture. So what equivalence means is, suppose I have some string X and sigma star, and I have two states. I have states P and Q. And now I'm saying that these states are equivalent. Okay, so I have P as a state and Q as a state. Then what my definition is telling me, it's telling me that if M starts at P and it reads X, and M ends in an accept state, then so will Q, right? Notice that these two states don't need to be the same, they just have to have the same type. Okay, so in other words, in this case, they have type accept. Or, right, so this is in the case that they're both, the destination states are both accept states. The other case could be that in both cases, I end up in not an accept state. So the idea is that P and Q are equivalent if for every input string where you give that input string to the machine and you ask it to start at either P or Q, the destination states have the same type. And by type, I mean they're both accept states, so let's double circle that, or they're both not accept states. Okay, so that's what I mean by equivalent states. And so what you'll notice, if we just go back quickly, so give me 2 seconds if you're writing this down. If we go back quickly, we notice that actually this state here and this state here were in fact equivalent. Why? Because imagine I start at this state and I read some string and I don't accept it. Maybe I end up here. Then if I read that string from this state, then I end up here, right? So there's kind of this symmetry. So in this case, I don't accept, and in this case, I don't accept. But if instead I start here and I do, end up in an accept state, so maybe I end up in Q3, well, then from here, I'll also end up in an accept state. So this sort of intuitive notion that these two states were serving the same purpose matches the definition, which is good, right? That's what you want. Otherwise, this definition would be useless, and that's not good. Okay, good. So those are equivalent states. That's the definition of equivalent states. Now, a fact about this relation, because this is really a relation between states. So a fact about this relation, this squiggle relation, is that given some DFAM, this relation is an equivalence relation. And I will not prove this because you've done enough proving of equivalence relations in assignment 1. So you can check this. It's a very easy proof. It's like 3 lines. So there's an immediate implication, though, is that because this relation is an equivalence relation, that means that if I have some state P in Q, then P belongs to an equivalence class of this equivalence relation. So I have P is an equivalence class, of this relation. Okay. And so notice what I said at the beginning of class. I said that what we would do in the minimization algorithm is we would take states which serve exactly the same purpose, and we would collapse them together, right? Well, this collapsing, it turns out, is exactly this equivalence class, right? What we're going to do is we're going to take all the states which are equivalent to each other and then collapse them into an equivalence class. So the equivalence classes, of this equivalence relation will become the states of the minimal DFA. That's what the minimization algorithm is going to return. It's going to return a DFA which has as states these equivalence classes. Okay. So now we just have to sort of show how this is going to be done. But before I do that, I think I'd like to just illustrate that a bit. So what did I just say? I said the goal of the minimization algorithm will be the following. It will be to make states in a minimal, for now, let's say it's not unique, a minimal DFA M prime, the equivalence classes of this equivalence relation. Okay, so that's what we're going to do. So what does this really look like? If I illustrate this again, like I said, I enjoy pictures. So this is M, and this is the start state. So maybe I'll call it Q0. Then I have some other states. I have Q1, Q2, Q3, Q4, right? So then my set of states Q is, Q0 all the way to Q4. And now I have an equivalence relation, right? I have an equivalence relation, in particular this relation, that's applied to the set of states. So what this equivalence relation does, right, it creates equivalence classes, but remember, equivalence classes partition the set of states. So what's going to happen is, for instance, these two states, are going to be in perhaps this equivalence relation, equivalence class, come on. Then these states are going to be in this equivalence class. And then this state maybe is in a singleton equivalence class. So this is what the minimization algorithm is going to do. It's just going to take states which are equivalent and it's going to collapse them together. Okay. So you might be thinking, well, this is all well and good, but now that I've collapsed my states, how does my machine actually behave, right? So if my machine M prime, which is a minimal DFA, is in this state, right? What that means is that this is the equivalence class containing this state and this state. What happens if this machine reads a letter, right? Well, if this machine reads a letter, then what it'll do, it'll simulate reading a letter from Q1 and from Q0. But now, is it possible, right, for this to be a well-defined or well-constructed machine? It shouldn't happen that, for instance, Q0 when I read an A goes here, and Q1 when I read an A goes here, right? That shouldn't happen because that would sort of break the determinism of my machine. And so what we'll show in the following lemma is that that doesn't happen. And if I have states which are equivalent and I read a letter from either of those states, then I end up in the same equivalence class. So that's what I'm going to show in the following lemma. So let's call this lemma A for array. So given some DFA M and a pair of states, well, I guess I need a pair of states here. A pair of states which are equivalent. Oh, Mark is here. Excellent. So I have pairs of states which are equivalent. What this lemma is saying is for every input letter, if I start at P and I read sigma, then this will be in the same equivalence class as if I start at Q and I read sigma. Right? And this is to be expected, right? You want that if your machine has as states equivalence classes and it reads a letter, you want it to always end up in the same equivalence class. And this is telling me that this is true. But now I need to convince you, right? Let me do the proof and then I'll get to you. So I need to convince you that this is true. So let's do a quick proof. So this proof is going to be hopefully very short. So suppose I have two pairs of states, and let's assume that they're equivalent, right? Now let's pick some input letter, sigma. Let's pick some input letter, sigma. And let's suppose for the sake of contradiction, that the conclusion in my lemma is false. So suppose that this is not true. Where's this? Good. So suppose that this is not true. Okay. Well, remember, for two states to be equivalent, right? For two states to be equivalent, whenever you read a letter from either of the states, the type of the destination states has to be the same. But what I'm saying here is that for at least one input string, the type of the destination states is different, right? For these two states, right? Because remember, these are states. Okay, so let's draw that out. So suppose I have this state and this state. Okay, and suppose I have this input string X, which causes my destination states to have different types. So maybe this destination state has type not accept, and this one has type accept. Well, what does this really mean, right? What this really means is, remember, to get to these two states, I needed to read a letter sigma. So from Q, I needed to read sigma, and from P, I needed to read sigma. So now what's happened is I have an input string, namely sigma X, for which when I read sigma X from Q, I end up in an accept state, or not an accept state. And then when I read sigma X from P, I end up in an accept state. So I have a string where when you read it from either Q or P, the type of the destination states don't match. And that's a contradiction because I initially supposed that P and Q were equivalent. So I have a contradiction. This is my nice little symbol for a contradiction. And that completes the proof. Okay. Owen, you had a question?
Yeah, so is equivalence therefore implied by the transition function?
Is equivalence is no, it's not. Oh, hang on. So the question is equivalence implied by the transition function? And I mean, yes, it's in the definition, right? So it says that these two states are equivalent if you take any string, right? Take any string and give that string to the transition function, the extended transition function with input parameter px and qx, then the type of the outputs has to match, right? The type of the outputs either has to be accept states or non-accept states. Yeah, good question. Yeah, good. Okay, good. Yeah. That's okay. Yeah. As long as the type is the same. Yeah. So the question was, what if these two states are different? It's okay as long as they're accept states or non-accept states, as long as they have the same type. Yeah, good question. Okay, excellent. So this completes this proof, right? This lemma, the proof of this lemma. And the immediate implication to this, so the implication here is what I was talking about beforehand when I was saying, well, is this machine well-defined? Well, now it must be, right? Because if I take two states P and Q from this equivalence class, then for any input letter A, the output of the transition function when the machine from Q reads A and when the machine from P reads A, these two output states will belong to the same equivalence class. So namely, let's call it this equivalence class. I just picked this representative, but I also could have picked this one. So that means that in the explicit construction, which I'll give now, we have a well-defined machine. Okay. So let's now give the explicit construction of M prime. Okay, so notice what I'm doing is I'm sort of talking about the minimization algorithm without actually presenting it. I'll present it at the end. The reason why I'm doing it this way is because if I had presented at the beginning, then I would have had to say at every step, okay, I'll explain this in 30 minutes. So that's not ideal. So I'm going to show you what the output is going to be, and I'm going to prove to you that the output is correct. And then we'll see how the algorithm actually gets to that output. Okay, so explicit construction of M prime. This is also sometimes known as the quotient construction. So given some DFA M, which I'll represent explicitly, we define a new DFA M prime, which I'll also denote explicitly as the following. So like I just said before, the set of states of this new DFA M prime, so the set of states Q prime, are going to be equivalence classes of this equivalence relation that I just defined. So they're going to be the states in the original machine Q, where you take those states and you put them in equivalence classes of that equivalence relation. So I'll denote this as Q sub this little squiggle. Okay, so that becomes a set of states, right? They're equivalence classes. Now, what is the start state? Let's see, let me ask, what's a good choice for a start state here? Louis, yeah? Yeah, good. So it's the equivalence class which contains S0, right? And so this makes sense. This is kind of how we did it with the conversion from NFAs to DFAs. We said the state of the DFA that contains the set which contains the start state is the start state for that DFA. So it's a similar idea here. Okay, now what's going to be the set of accept states? The set of accept states is going to be, what you're going to do is you're going to take all the set of accept states from the original machine and then place those into equivalence classes of this equivalence relation. So let me make it explicit to show you that this is an equivalence class for this equivalence relation. Okay, so this is the setup. The last thing I need to do is I need to define the transition function. So delta prime, when delta prime is given a state and a letter. So now remember, this state is an equivalence class. Then what it'll return, it'll just return simulating the machine M. So it'll simulate the machine N when reading A from Q. And then it'll augment that with the equivalence class of that equivalence relation. And we just saw, thanks to the lemma, that this is well-defined. So this is well-defined thanks to lemma A. So what do I mean by well-defined? Well, I mean that, here, this is an equivalence class, right? So it just so happens that I picked Q as its representative. But what if I had picked P, right? P would have also been a good representative for this equivalence class because it belongs to that equivalence class. But what my lemma tells me is that if I transition from P reading A, then I'll end up in the same equivalence class. So these two things will be the same. And so that's what I mean by saying that the machine is well-defined, or the transition function in particular is well-defined. Okay. So now that I've given you the explicit construction of M prime, this is what the minimization algorithm is going to output. I need to show you that this is a correct output. So I need to do two things. The first one is to prove that the language accepted by M prime is exactly the same as the language accepted by M. If this was false, this would be a very useless minimization algorithm, right? Because then you would have broken the actual mechanics of your machine. So this needs to be true. And the other thing is M prime needs to be minimal, right? I'm claiming that it's minimal, but I need to prove that to you. So I'll do each of these one by one. So for the first one, I need to show you a few lemmas before I get to the statement. So the first lemma I need to prove to get to this statement here is the following. If I have two DFAs, M and M prime, and I have some state P in my set of accept states of the original machine, then for any other state in Q, if P is equivalent to Q, then Q must also be an accept state. Okay. So why is this lemma true? Well, the proof is actually not too difficult to see. But actually, maybe before I give you the proof, let me just quickly say what the intuition is here. What this lemma is actually saying, is if you take a state which is an accept state, and you put that into an equivalence class that contains accept states, then it's only going to contain accept states. So any of the other states which are equivalent to P will also be accept states. That's what it's saying. Okay, give me one moment. So let me write that. This is saying that the equivalence classes of M prime, which contain accept states, of M, only contain accept states of M. Only contain accept states of M. Okay, so this is what verbally or sort of in natural language this lemma is telling us. So the proof for this, it's also not that bad. Suppose I have some state P, which is an accept state, and I have any other state Q. And let's suppose now that P is equivalent to Q, right? So that's the premise of the lemma. Then again, let's assume for the sake of contradiction that Q is not an accept state. So what's going on here is I have one state which is an accept state and another state, which is not an accept state. So why is this not possible? There's a contradiction here. Yeah.
The empty string.
Excellent.
And one would be accept state.
Excellent. Very good. Thank you very much. So the reason why this is impossible is because if from P the machine reads the empty string, it'll end back in P. But if the machine from Q reads the empty string, then it'll end back in Q. But in this case, the type of the destination states don't match. So the type of the destination states don't match. This is an accept state, this is an accept state, and this is not an accept state. So again, we have a contradiction. And again, this completes the proof. That's nice. Yeah. Ah, very good question. So the question is, does that mean that all the accept states are in the same equivalence class? No, that isn't true. No. I'll let you think about why. Yeah. But that's an excellent point. So the implication of this lemma is the following. It says that if P is an accept state, then it will be the equivalence class which has as P a the equivalence class which has as P its representative will be an accept state in F prime. Okay. And so these things are equivalent. This is the implication of this lemma. Okay. So that's the first lemma we need to prove the correctness of the machine. The other one we need, I'm not going to prove because it's by induction. And you have more than enough inductions in assignment 2. But what this lemma is stating, it's stating a relationship between the extended transition function of m prime and that of m. So it's saying that in m prime, if you read a string w from the equivalence class with representative p, then what you could do to find out the destination state is you could just simulate m starting at p and reading w and taking that equivalence class. So hopefully this is intuitive. So this is lemma C. The proof for this is by induction on the length of w. And so for that, I'll just skip that because it's not very interesting. Okay, but now with lemmas B and C, I'm able to prove the following theorem. I'm able to prove this following theorem. So given DFAs m prime and m, so these are DFAs, the language accepted by m is exactly equal to the language accepted by m prime. And so m prime as constructed above. So why is this true? So the proof now is 5 lines because we've done all of the work in the 2 lemmas. Suppose I have some string x in sigma star, and suppose that x is in the language accepted by the machine m. Then by definition, that means that in m, if you start at the start state and you read x, then you end in a final state or an accept state. But then by lemma B, what this means is that if I end in an accept state of my machine M, then the equivalence class of that state will be an equivalence class that is an accept state in my machine M prime. Yeah. So that means that this thing here, augmented with the equivalence class, is in F prime. So this is by lemma B. Lemma B. And then by lemma C, we know that by lemma C, we know that we can just rewrite this as the following with the extended transition function of m prime. Okay. And so now what I've done is I've rewritten things such that I'm talking about the start state of m prime, the set of accept states of m prime, and the extended transition function of m prime. Right? And so then by definition, this means that x is in the language accepted by m prime. And that completes the proof. So this clearly shows that the language accepted by m is equal to the language accepted by m prime. Good. Okay. So the other thing I'd like to do is I'd like to show why m prime is minimal. So I have the following claim: m prime is a minimal DFA. Okay. So this proof is going to use a proof technique that we actually already saw. So that's why we already saw it, actually. So what is this proof going to look like? Well, we're claiming that m prime is a minimal DFA. So let's suppose that m prime has n states. So really, this should be a proof by induction on n, but I'm not going to do that because that's not very interesting. But suppose that m prime has n states. Okay, so it has n states, and suppose that these states look like this. So they're equivalence classes, and suppose their representatives are Q1 all the way to Qn. Now, for each of these equivalence classes, I'm assuming that these states are reachable, right? I'm assuming that these states are reachable. So that is that from the start state of my machine m prime, I can reach each of these states with some string. So perhaps x1, x2, and xn. So why is this true? Because I'm assuming that m to begin with had no unreachable states. I can assume this safely because if it did have unreachable states, then I could just eliminate them and I would get a smaller machine which accepts the same exact language. So I can assume that M and therefore M prime have no unreachable states. Okay, so then each of these n states can be reached from the start state with at least one string. In this case, I name them x1, x2, all the way to xn. Okay. So now note that, of course, what I'm also implicitly assuming is I'm assuming that these states are different, right? So that the equivalence classes are different. So if I'm saying that these states are different, then what this implies that the representative of these states are not equivalent, right? So if the representative of these states are not equivalent, what does this mean? By definition of equivalence of states, that means that there exists some string in sigma star such that if you read that string from Q1, then perhaps you end up in an accept state. But if you read that string from Q2, then you don't end up in an accept state, right? Or vice versa. But let's assume without loss of generality that this is the case we're dealing with. We don't lose any generality because you just have to sort of swap the accept and not accept states. Okay. So that means that there is at least one string x where this is going to hold. So why is this interesting? Well, because now I can notice the following. I can notice that in my original machine M, right? In my original machine M, I could get to Q1 by starting at S0 and reading X1, right? So I could get to Q1 by starting at S0 and reading X. So this would be Q1. And then from there, right? Oh, X1, sorry. And then from there, if I were to read this string X, right? So this particular string X, then as you'll show in assignment 2, this is the same as starting in the start state and reading the string x1x. Okay. But what do I know? What do I know about this state here? Owen, maybe? No. Yeah. What do I know in terms of its type? It's an accept state. Excellent. So I know that this state is an accept state. And I know that the machines are correct, right? So this implies that x1x is in the language L that the machine accepts, right? So it is in L of M, which is equal to L of M prime, right? Okay, I haven't done anything crazy. And you can say the same thing about the other string x2x. So similarly for x2x, we can use the same argument. So if you start at S0 and you read x2, you end up in Q2. And then from Q2, if you read x, remember, when I say x, I mean, maybe I should make this explicit. So this x and this x are the same, and they're the same as this particular x, which allows this statement to be true. And so because that's the case, and because I know that this left-hand side is equal to this right-hand side, I know in this case that x2x is not in the language accepted by M because this is not an accept state. Right? So we just showed that the language accepted by M is exactly equal to the language accepted by M prime. Okay, so far I've been seems like I've been sort of mindlessly wandering this proof. What's the point here? Well, here's the punchline. Let's consider some arbitrary DFA M prime, let's say M double prime actually, such that the language accepted by M double prime is equal to the language accepted by M prime, which is the same as the language accepted by M, right? Now let's label the states of M double prime. So label these states. Let's label them in the following manner. Hopefully this looks familiar to you. The state that X1 reaches, I'll label A. The state that X2 reaches, I'll label B. The state that Xn reaches, I'll label N. Okay, so here I'm labeling N states, right? Maybe I've labeled the same states twice. So maybe A and B are the same state. Maybe I just called them two different names, right? Well, let's check that that's not the case because it won't be. So is it the case that I've sort of relabeled the same state twice? So is it possible that A is in fact the same state as B? I think I'll answer that myself. So no, it's not possible. No. Why? Because if I start at the start state and I read X1, then I go to A, right? Now let's suppose that A and B were actually the same. So A was actually the same as B. So that means that X2 also ended up in the same state. And now let's extend the string. Let's extend the string in particular with the same string here, X. So I extend the string X1 with X. Then I know that X1X is in the language accepted by M prime and M. So that means it should be in the language accepted by M double prime, right? Which means that this should be an accept state. But on the other hand, I know that X2X is not in the language accepted by M prime. And so it shouldn't be in the language accepted by M double prime. And so then this state should also be not an accept state. So clearly I have a contradiction. I have a state which is both an accept and not an accept state. This is in the quantum world, and so this is impossible. So I have a contradiction. So this is not possible. And you can sort of repeat this argument for n choose 2 times, and you'll see that for any machine M double prime, it must have at least the number of states of the machine M prime. Okay. Yeah. Good. All right. Any questions about this before I move on? I'm sure you have questions, you just don't want to ask. Yeah. Yeah. Yeah.
How is it that it's the same X we use to define X1X and X2X and proclaim them to be accept states, non-accept states, but then
Right.
it's other arbitrary DFA, and we can say that this same string X, character X,
Yeah.
applied to this DFA.
Yeah.
Either accept state or not an accept state from the same.
Yeah. So yeah, let me try to summarize the question. I think the question is, well, what the hell, man? Why can you say that X is the same as X is the same as X is the same as X? I think that's what you're kind of saying. Okay, that's a very good question. So I haven't done anything magical. The only thing I've done is I've sort of used the definition of what it means for two states not to be equivalent. For these two states not to be equivalent, there must be at least one X, right? For which this is true. So now take that X and sort of store it in your head. So I have that X in mind, right? It's a string, right? So I'm not talking about states or anything. I'm just talking about a sequence of letters, right? So I have some sequence of letters. Now I know that my machine reads these strings, right? I know that my machine reads these strings. So in particular, it could also read that string extended with that string that I had in memory, right? Because these are just sequences of letters. So that's okay. And then again, here, So then again, here, it's true that I'm talking about an arbitrary machine, right? But I'm talking about these particular strings, right? And these are the particular strings from before. Right? So the only thing that's really going on, and I think the reason why this proof might be a bit confusing at first is because it's quite long, right? So you have to sort of convince yourself that the thing that I named at the beginning is the same as the thing that I named at the end. So these strings are the same. They just sort of follow through from the start to the end. So everything I'm doing here is very legal. If it wasn't, then I'm sure there would be a math student here who would be yelling at me. And I'm not getting that, so that means I'm okay. Yeah? Okay, good. It's a very good question. All right, let's move on. If there are no other questions, which it doesn't look like there are. Right, okay, so I misjudged the number of pages I needed. So at this point, you might be asking yourself, well, Cesare, who cares? This has been very boring. Why do we have to talk about all this? So like I said at the beginning of the class, I'm talking about what the minimization algorithm will output, right? Because I don't want to sort of show you the algorithm and then convince you that the output is correct. So I've sort of done things backwards, but at this point, right, at this point, we're actually ready to show you what the minimization algorithm looks like. And I've sort of been lying to you since the beginning of class, because I sort of gave you this impression that the minimization algorithm, what it does is that it takes states, so it picks one state and another state, and it collapses them together. So the minimization algorithm doesn't quite do that, because that's actually quite hard to do. What it does instead is it says, okay, imagine that all the states were in the same equivalence class, and then break up that equivalence class until you get the correct partitions. So that's what the actual minimization algorithm is going to do, and I'm going to write that here. So the way the minimization algorithm actually works is the following. So the first thing it does is it merges all the states of M together. And the second thing it does is that it keeps splitting the machine, by finding states which are not equivalent, or this more technical term to talk about states which are not equivalent is the term distinguishable. So you can distinguish between the states because they're not equivalent. So you keep splitting the machine based on the fact that you have distinguishable states in the same partition until you can't split any further. So until you can't split any further. Okay. And so let me actually quickly define what distinguishable means for our purposes, because we're going to talk about it a few times for the rest of the lecture. So if I have this DFA M, which again I'll define explicitly, and I have pairs of states, then we say that P and Q are distinguishable which we write P bow tie Q if P is not equivalent to Q, or in other words, to write this out explicitly, there exists a string X, which we'll call the distinguishing string. The distinguishing string, such that if the machine starts at P and it reads X, and it ends in an accept state, then it won't end in an accept state if it reads the same string from Q, or vice versa. Or vice versa. Okay. So this is what distinguishable means. And what the algorithm is going to do, what the algorithm I'm going to present right now is going to do, it's going to find pairs of states which are distinguishable, and it's going to split them apart. So it's going to say these two states can't belong to the same state in the minimal DFA. But before I do that, I'd just like to remark a fact which the minimization algorithm is going to leverage, which is if there is a letter such that delta PA is distinguishable from delta QA, then the states you had started with, P and Q, will also be distinguishable. So I'll talk about that when we show the correctness of the algorithm at the end of the class. Ooh, 20 minutes. All right, so I'm going to show you the minimization algorithm. For those of you who are using a notebook, well, like for those of you who are using pen and paper or pencil and paper, what I recommend is to use one page for the state transition diagram and a table, and the other page for the steps. If you have an iPad, then you're much luckier and you can do what I'm going to do now. Okay, so I'm going to show you the minimization algorithm. So I'm going to show you the minimization algorithm. But to showcase the steps, I'm going to use an example. And so the example is going to be from the start of class. So recall this beautiful DFAM. So this is my DFAM, which I'd like to minimize. Okay. So the first step of the minimization algorithm is you start with this DFAM, with this input DFA. And step one is to remove the unreachable states. Right, so you run depth first search, starting from the start state, and you mark all the states that you visit. The states that you don't visit, you just throw them out. So in this case, I'll throw this guy out, and this guy out. And so as a result, I'll get magically this machine. So this is a machine that results from step one. What do I do in step two? In step two, oh, I'm supposed to label the states. Thank you, myself, telling you that. So step two, what I'm going to do is, based on the state transition diagram that's left, I'm going to make a 2D array of size Q by Q, or cardinality of Q by cardinality of Q. Of course, I'm talking about Q without the unreachable states. And the goal of this array is it's going to start as an empty array, and it's either going to have a 0 or a 1 in its entries. So if the entry of this array, which corresponds to the entry for the pair of states P and Q, is 0, then the goal is that P will be distinguishable from Q. This is the goal. This is what the algorithm is going to try to do. So I make my 2D array. This is my 2D array. Very nice. Imagine if I'd done this in front of you. That would have been bad. Okay. So this is my 2D array. The other nice thing about this algorithm is that I don't really need all of the array. I just need half because the argument is symmetric, right? So if I'm saying that Q1 and Q0 are distinguishable, then so will Q1 and Q0 here. So I'm only going to use the bottom half of the array. Okay, good, excellent. So now I can move on to step 3. What is step 3? So step 3 is the following. Oh, you can't see the, oh. Okay. Step 3 is the following. For every pair of states, P and Q, where P is an accept state and Q is not an accept state, or vice versa, let's mark the array with the entry PQ as 0. Why am I doing this? Because already if I have a state which is an accept state and another state which is not, then of course they must be distinguishable, right? Because in particular, if I read the empty string from P and Q, I end up in states which have different types. So let me do that here. Let's see, what are the pairs of accept and non-accept states? Well, it's Q0 and Q1, so this will be a 0. So will this and this, this and this, and this and this. So far, so good. I'm just filling up a table. Step two is make the table. Yeah. Okay, good. Excellent. So that's step three. Now step four is going to be the recursive or the looping case. Let me get to you at the end, Owen. Yeah. Unless you can't see. Is it that you can't see?
Yeah.
Oh. Why is it doing that? Stupid. Zoom out more. Okay. All right. So this is step three. Now step four is going to be the case where we're going to loop. So I'm going to scroll down. Okay. So this is step four. Step four, I've replicated the machine, the array. But what is step four going to be? It's going to be for every pair of states P and Q, if there is a letter such that the entry of delta P sigma and delta Q sigma is 0. So those two states are distinguishable. Then their original states should also be distinguishable. And so what I'll do, I'll mark P and Q also with 0. Okay. And so what I'm going to do is I'm going to repeat this step. I'm going to repeat step four until A does not change. Okay. All right. So let's test this out. Let's test this out. Oh, this is very annoying. Okay. So let's try a couple of cases of pairs of states. So for instance, let's say state Q3 and state Q0, right? So what I need to do is I need to check where those states go for every input letter, right? So if I'm at Q0 and I read a B, well, I know that I end back at Q0. And if I'm at Q3 and I read a B, then I end back at Q3, right? So is Q0, Q3 already marked with a 0? Well, no, that's this cell, right? That's this cell. So this isn't evidence that I should mark this cell with a 0. So let's try again with A. Let's try again with A. If I'm at Q0 and I read an A, then I go to Q1. And if I'm at Q3 and I read an A, then I go to Q4. Okay. Is Q1, Q4 labeled with a 0? Q1, Q4 is not, so there's no 0 here. And so that means that that's also not evidence that I should mark this entry with a 0. So I just leave it empty for now. Okay, let's look at another example. In particular, let's look at Q1, Q2. So for Q1, Q2, if I'm at Q1 and I read an A, I stay at Q1. And if I'm at Q2 and I read an A, I stay at Q2. Okay. Well, Q1, Q2 is, again, this entry, which isn't marked with a 0. So that means that that isn't evidence that I should mark this guy with a 0. So let's try again with B. Let's try again with B. If I'm at Q1 and I read a B, what happens? I go to Q2. And if I'm at Q2 and I read a B, then I go to Q3. So I need to look for the entry Q2, Q3. So Q2, Q3 is Q2, Q3 here. It's marked with a 0, right? So I have to mark this entry with a 0. Okay, there's many questions. That means I must have made a mistake. Give me 2 seconds. So I mark this with a 0. Yeah, what's the problem? Oh, you're right. Oh, absolutely. Damn. You're right. Absolutely. Very good. Thank you. So, yes. Okay, but the idea is still the same, right? So if you read a B, you stay at the same place. If you read an A, then you go to the other states. Thanks very much for the correction. Okay. Good. Okay, thank you. Okay, and so I'm not going to redo that for every single pair. So you'll have to trust me that the entries that I'm going to mark are going to be for this iteration, this one here, and this one here, and also this one here. Okay, magically. Okay. So I repeat this, right? So this is the first pass. Now, again, I'm going to do the same thing. Ah, nice. These are already filled in, right? So I'm going to repeat the same thing. And I'm going to continue doing this until the array doesn't change, right? And so it turns out that at this pass here, the array is no longer going to change. So step 6 would be, or step 5 would be continue until no change. Well, there isn't going to be any change. And that kind of makes sense, right? Because we already know intuitively that Q0 and Q3 are equivalent, right? And so it makes sense that if you go through the same pass again, Q0 and Q3 aren't going to be marked with a 0. And so you continue until no change. And then once that happens, so once you have no change, mark all other entries with A1. Okay, so for instance, this guy gets a 1, this guy gets a 1, and this guy gets a 1. So now the last thing is actually building the machine. The last thing is building the machine. So that's step 6. So step 6 is building the machine. So the way I build a machine is I take the pair of states which are marked with a 1, and I put them together in a single state for my minimized DFA. So for instance, in this case, Q0, Q3 are marked with a 1, so they should go in the same state. Maybe there's more, maybe there isn't. Then Q1, Q4, those are marked with a 1, so those should go in the same state. Maybe there's more, maybe there isn't. And then again, Q2 and Q5 should go in the same state. So Q2 and Q5. So you'll notice that at the beginning, I've started by having these sets with only the sort of left curly brace. That's because maybe I can add more states here. But now I've sort of exhausted all the states, right? I only have 6 states, and I've placed them all in separate sets. So I can close all my sets here, and I make each of these states of my machine. And now the state, which is going to be the start state, is the one that contains the start state from the origin machine, right? So that's going to be this one. The accept states are going to be the states that had accept states from the original machine. Again, that's going to be this one. And then the transition functions, I'm just going to use the transition functions from the original machine and apply them to each of the states in my set. But because I know that these guys are equivalent, right? When I read an A from Q0 or Q3, it's going to go to the same partition or the same equivalence class. So that means that if I read a B, I'm going to go back to myself. If I read an A, I'll go here. I have self loops for my Bs and A's that go around. Okay. And so this is exactly the machine that I would have built had I asked you to create a machine that accepts strings where the number of A's is divisible by 3. Okay. Yeah. Louis? No. Because then it would just be in its own set. Yeah, because you take pairs of states. So then imagine you had an extra state Q6, right? Q6 would have been zeros with all the other pairs, right? So then the procedure is, if that's the case, then just take Q6 and place it in some other set, some other partition.
Okay.
Yeah. So definitely building the machine that could be much more verbose. So I agree that maybe there's a few steps missing, but the idea should be more or less obvious. Yeah, Jude.
Question for the finding the letter, like, if there exists the letter.
Yeah.
Algorithm.
You just go through each letter. Yeah. Yeah.
For every.
Yeah. State for every pair of states. So it's not very efficient. Yeah. Okay. Good. I need to show correctness, but then maybe ask me a question at the end of class. Because what I'd like to do with the 5 minutes that I have left is I'd like to prove to you that this algorithm is correct. And so I'm going to do that in the following lemma. So the lemma is going to be crucial to proving that this minimization algorithm is correct. So given the minimization algorithm described above and some input DFA M, then for every pair of states, if the entry of A with P and Q is marked with a 1, then P and Q will be equivalent, and this is an if and only if, right? So if this is true, then this will show that the algorithm is correct, right? Because it'll show that it's doing what I claimed it was doing. So the proof for this is also not too bad. So suppose I have some DFA M, which I'll write out explicitly. Okay. And suppose, for the purposes of contradiction, that I had a pair of states which were marked with a 1, right? So a pair of states which were marked with a 1, but which were not equivalent, right? Which were not equivalent. So let's call this pair of states, let's call this pair of states a bad pair, right? Very bad. It's a bad pair of states. Okay, so if P and Q is a bad pair, that means that P and Q are not equivalent. So then, therefore, P is distinguishable from Q, which means that there exists a string X, which distinguishes P and Q, right? So now what we're going to do is we're going to say, okay, well, I know that I have at least one bad pair and at least one distinguishing string. Let's collect all the bad pairs and all the distinguishing strings. So what we're going to do is we're going to collect all bad pairs and all distinguishing strings. And what we're going to do is we're going to pick the shortest string. So we'll pick the shortest distinguishing string. Let's call it X. X is a distinguishing string, so it distinguishes between pairs of states. Suppose those states were, again, P and Q. Okay. Now, X is a string, so that means that it's a sequence of letters, A1, A2, all the way to AN, where each of these AIs is a letter from the alphabet. The number of letters in the string, so N, must be strictly greater than 0. So in other words, X can't be empty. It can't be empty because if it were empty, then P and Q would be a bad pair of states, right? But it would be a bad pair of states where P would be an accept state and Q would be not an accept state. But my algorithm deals with that in step 2 or 3, step 3, right? And so clearly X can't be empty. So X can't be empty, right? So this is true that N is strictly greater than 0. So now what we'll do is let's consider taking the state P and reading the first letter out of that distinguishing string. So that gives you some state P prime. Then taking the state Q and reading again that first letter A1. That gives you some state Q prime. Now it must be that P prime was distinguishable from Q prime. Why? Because the remaining part of the string is a distinguishing string for P prime and Q prime. So we have a distinguishing string between P prime and Q prime, right? So because A2 to AN is a distinguishing string. So we have a distinguishing string, but P prime and Q prime can't be a bad pair. They couldn't have been labeled 0 by the algorithm. They couldn't have been incorrectly labeled by the algorithm because A2 to AN is a shorter string than the shortest possible distinguishing string, right? So that means that, whoops, oh God. So this means that P prime and Q prime is not a bad pair. Get that out. Not a bad pair. Since, like I said, A2 to AN is a shorter string. And so therefore, the algorithm should label A, P prime, Q prime with a 0. So now I have A, P prime, Q prime, which is labeled with a 0, but that corresponds to delta P A1, delta Q A1. And so in my algorithm, what my algorithm does is it takes pairs of states, and then it checks for each letter whether A, this state, and this state is marked with a 0. And so it will see that that state was marked with a 0, that pair of states was marked with a 0 for the array A. And then in the algorithm, it will mark, so then the algorithm will mark A, PQ as 0 as well, right? And so that means that I actually didn't have for P and Q a bad pair. So I have a contradiction, so I don't have any bad pairs. And so that proves the forward direction. The backward direction is almost by definition. And you can use the lemma to immediately show that the algorithm is correct. Okay, thanks very much. See you on Thursday.